Hey friends, so awkward. When I was actually in class with you guys covering these notes, I I really have no idea what happened, but for whatever reason the iPad did not record the lecture. So I am recording this after the fact. I'm just going to go through the lecture one more time. Obviously, it won't be as much fun because you won't hear me talking with members of the class at the same time as writing the notes, but at least it'll have the same content. So here we go. Today we're talking about the time responsive systems. This is our second lecture on the time responsive systems. Last class we talked about first order systems, and this class we're going to mainly focus on second order systems. Just for continuity of content, though, I am going to spend a little bit of time reviewing the first order time response of systems. And you'll probably see why. There are a lot of parallels between last class and this class in terms of what to keep an eye on. So let's review. Last time we talked about a very, very simple block diagram where we have an input R of S and an output C of S. And in this block here, we have the plant model or a transfer function G. And if you remember, we said that there is a general form for first order system transfer functions. And we said, if you have a first order system, you will always be able to write it as the transfer function G of S is equal to some constant A over S plus A. Okay. Let's look at an example real quick. Let's say we had G of S equal to maybe 4 over S plus 2. So the first thing you might notice is, I don't have the same constant in the numerator as I have in the denominator. Up here there's a 4 and down here there's a 2. So what gives, Dr. Higgins? Is this in the general form or is it not? And if you think back to last lecture, we went through a little bit of a song and dance to try to figure out if we could get this to look more like this. And so what we said is we could write this in its equivalent form of 2 times 2 over S plus 2. And this obviously is the same thing as what's over here. But we now just have a constant multiplied by a transfer function that looks more like our general form, where we have a 2 in the numerator and a 2 in the denominator. So for this transfer function, the value of A equals 2. And so what we talked about is that multiplying our transfer function by a constant does not change our time response characteristics. It only changes the amplitude of the response. So let's draw out the time response of this system. C of t. Oops. Oh, goodness. Our output with respect to time. And we said, okay, for a first order system, if I get a unit step input, it's going to go from our initial condition, which is 0 for our transfer function. It's going to approach that step input of 1. And we said that our time constant tau is the time it takes for our response to get within 63.2%, so 0.6. Good gracious, iPad's not happy today. So over here we had tau. And we said, okay, what happens if you multiply by 2? what happens if you multiply by this 2? Well, we still reach 63% of our total response by tau, by time tau, same time constant, but our amplitude is twice what it used to be. So if 63% of 2 is maybe somewhere up here, we still reach that value at time constant tau. Looks something like that. So this stays the same, but the amplitude of our final value is multiplied by 2. All right, so I'm just going to make a note here that multiplying by a constant gain does not change the time response characteristics. Okay. All right, let's do a little bit more review. Let's clean this up just a little bit. Let's look at this transfer function g again, this general form. Let's try to convince ourselves that this is indeed LTI. If a system is LTI, we should know that the transfer function should end up looking like a polynomial over a polynomial. Is that what we have for g of s? Absolutely. We have a polynomial in the numerator, and in fact, it's a polynomial in terms of s, but there's a 0 coefficient in front of the s term in the numerator. And the denominator is a polynomial in terms of s, where s is multiplied by 1 plus a constant. So we do indeed have a polynomial over a polynomial. That's great. That's an indication that this system is LTI. And then the other thing I want to review is how do we tell what is the order of our system based on the transfer function? And so I can absolutely confirm that this thing is a first order system. And the reason is because of the exponent, the highest exponent of s in the denominator. So the highest exponent of s in the denominator is simply 1. Okay, now if I had had something where the denominator had an s squared term, maybe something like this would be a second order system because the highest exponent of s in the denominator is 2, and so on and so forth. If I added another term, maybe it was like 5s cubed, that would be a third order system. All right. So absolutely, we can say that this is a first order system because we only have the plain Jane s to the first in the denominator. Okay, now let's talk about the time response characteristics that we talked about. And then let's remind ourselves that for our time specifications, we always assume that we're analyzing the system's response to a unit step input. So for time specs, we always assume we are talking about the system's response to a unit step input. All right, and if we think about the Laplace transform of a unit step, we should know that that looks like 1 over s. So for all the time specifications of systems, both actually in the first order situation and for today's main content in the second order situation, we'll always be analyzing the system's response to a unit step input. So for our first order systems, let's look at the system's response. So let's look at the system's response to this input. Specifically in the time domain. It's a fancy way of saying that the x-axis of this graph is going to be time. And I want to look at the output with respect to time. And so he said first order systems are pretty plain Jane. They all have something that looks similar to this. First order systems do not oscillate. Only second order systems oscillate. Sorry, I should say systems only begin to oscillate at second order and above. Okay, so we're again looking at a unit step input here. And let's see, this 1 was our input. That was our unit step input. And we said the time specs are they're all a function of this time constant tau, which is 1 over a. And a here refers to this a in the general form of our transfer function. And this is our time constant. And we said this is the amount of time it takes for our system to get to 63.2% of the final value. So this is time tau, if I were to draw it on the graph. And then we also said that we have a rise time, TR, which is 2.2 over A, or equivalently 2.2 times tau. This is our rise time. And this is the time that it takes to go from 10% of the final value to 90% of the final value. So the time between here and here, here and here, is our rise time. And then lastly, we have a settling time, TS, equal to 4 over A or 4 tau. And on the graph, we said this is the time it takes for the response to reach within 2% of the final value and stay within 2% of the final value thereafter. And so 2% away from 1 would be 0.98. So if I draw something like this, and then 1.02 would be the higher end of that. So as long as we stay within this bubble of 2% of the final value, that is, we enter that envelope right here. So this is our settling time, T sub S. Sorry, I'm running out of room to write these tiny values. So this would be like 1.02, and this lower bound would be 0.98. 2% of the final value. Okay, that's all the review that I'm going to do for first order systems. And now we're going to talk about second order system response. And I'm going to try to be fairly parallel with the way that I covered first order systems. So I'm going to do the same thing as we did before, and we'll start with a really simple block diagram where we have R of S, we have our transfer function, that's some general form of a second order transfer function. And I have my output. So I could write this as some constant b over s squared plus a s plus b. Now my first question for you is, how many poles do we expect for a system like this? How many poles? Well, it's the same as the order of the system, right? So if I have an s squared polynomial, that means I have two roots, which means that I have two poles. Because remember, the definition of a pole is the value of s that causes the denominator to become 0, which is also the definition of the root of that polynomial. So second order system has two poles. First order system, only one pole. This is always the case. Okay. Now, this is one way to write the general form of this second order system, but we're actually going to look at a slightly different way of writing the general form. Now, they are completely equivalent, and we need to kind of be comfortable with seeing them in both ways. So I'll go ahead and hop right in. This is, of course, a transfer function, g of s, but I can also write g of s can also be written as omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Okay, now I say these are equivalent because we could simply say, that whatever b is, it's equivalent to omega n squared. See, because this is a b and this is a b. And then we could say that a is simply equal to 2 zeta omega n, right? Because whatever multiplies s in the denominator is the same as a. So these two things are equivalent. And the reason that I write it this way is because these values of omega n and of zeta are the values that have very clear control over the behavior of a second order system. And we're going to dive it really deeply into what happens as omega n changes, or better yet, what is omega n and what is zeta. So what you're going to see next is a deep dive on what is omega n, and then a deep dive into what is zeta and what are the effects of these two values on our system response. Okay, so first I'm going to start out with omega n, and so I'm going to say we call this thing, we say it as omega n. We call this the natural frequency of the system. Natural frequency. And we're going to talk a little bit about what the heck is a natural frequency. Omega n, or the natural frequency, is the frequency of oscillations in radians per second. So it's important to note that this is by definition in the units of radians per second. If there's no damping, without damping. Hint, hint, damping has to do with zeta. It's not exactly the same thing, but this is what happens when zeta is equal to 0. Okay, so if you think about a pendulum, if we think about a perfect pendulum that has no wind resistance, no friction, those sources of damping, none of that exists. If we take that pendulum and we release it from some non-zero initial condition, This is the frequency that pendulum is going to oscillate at. That will be the natural frequency of the pendulum. All right. Now, you might have heard a slightly different term that means the same thing. You might have heard this called the resonant frequency of the system. And in fact, those are the same thing. The resonant frequency. But resonance as a term specifically makes us think, or should make you think, about forcing the system at the same frequency as the natural frequency of the system. So I like to try to make this idea a little bit more concrete with two examples. So one is swinging, like at the park. Most of you know I have a 1.5-year-old daughter. We just got her a playset in our backyard, and so we're doing a lot of swinging between getting home from work and eating dinner. And so she's learning how to swing. She doesn't yet know how to reach the resonant frequency of the swing, so we have to do all of the pushing. But that's what you do when you're learning how to swing, is you inject energy into this system by forcing the system at the swing pendulum's resonant frequency. So you pump your legs at the same frequency as the natural frequency of this pendulum. Okay? Now, usually when we think about hitting a system's resonant frequency, a lot of times people will think, oh my gosh, that's really, really bad. And the reason that that's bad is for an undamped system, if you force it at the resonant frequency, what will happen is that your oscillations, instead of damping out, your oscillations will tend to grow over time and get bigger and bigger and bigger and bigger. So if you think about a mechanical system, if its oscillations are always getting bigger and bigger and bigger, this system is going to fail. There's going to be a lot of really high forces on this system, which often cause a mechanical system to fail. Okay, now this doesn't happen when my daughter is swinging and she pumps her legs at just the right frequency. The reason is because this is a damped system. And in the real world, it's almost impossible to get a complete, well, maybe I should say, it is impossible to have absolutely zero damping. In all actuality, there's friction, there's wind resistance, there's all sorts of energy losses that happen to any real system. So when my daughter pumps her legs, she is not usually able to, unless she just continues pumping and pumping and pumping and adding more and more and more and more energy, she cannot overcome the energy losses in this system. So she does not become an unstable system because the system has damping. However, this isn't always the case. It's not always the case that the energy injection loses out to the damping. And in fact, I usually like to talk about a particularly famous example of resonant frequency or failure due to resonant frequencies. And this is the Tacoma Narrows Bridge. Need to get a new pen tip on my stylus here. It's failing a lot. Narrows Bridge. So the Tacoma Narrows Bridge is a very famous example of a system that failed because it was being forced at its natural frequency. So what happened is this bridge was over some gap in terrain, and the wind that was blowing through this gap got blowing at exactly the same natural frequency of the bridge itself. So it started creating these oscillations in the bridge that grew over time such that the system failed. And so this huge architectural feat got ripped apart by the wind because it was forced at its natural frequency. So these are two examples of natural frequency. So swinging, we couldn't actually swing on our own without matching the natural frequency of the swing. So in that case, we used resonance to our advantage, whereas with the Tacoma Narrows Bridge, this was obviously a bad instance of hitting the resonant frequency, so that caused a failure. Now, I did say that this natural frequency is in terms of radians per second, but in other areas of engineering, we often hear of frequencies in a different unit. So I want to go ahead and give you the unit conversion there. So if you want the frequency in terms of hertz, this is equal to frequency in radians per second divided by 2 pi. Just in case you need to make that unit conversion. This is equivalent, of course, if you like to rearrange equations, this is the equivalent of omega equals 2 pi times frequency in hertz. Okay, so that's all I'm going to say about natural frequency. And now I want to do a deep dive on what the heck is that zeta term. Now, it's going to turn out that this zeta term is very influential over the poles of our system. And so we're going to look at some very special cases of the values of zeta and the effect that those values have on the overall behavior. And so I'll try to start out parallel to the natural frequency here. I'll say we call this thing, this symbol, we call it zeta. But this is the damping ratio. Okay, it is a ratio, and thus it is unitless. So it is not the same thing as the damping coefficient of, say, a dash pot. It's not the same thing. They are interrelated, but it's not the same thing. This damping ratio is unitless. And I said that it's very closely tied to the poles of our system. So let's start out by rewriting our general form for a second order system. We said this was omega n squared over s squared plus 2 zeta omega n s plus another omega n squared. So the poles of our system are those values of s that make this denominator 0. And so this is specifically for a second order system. We have a way to find the roots of a second order system, and we do that with the quadratic equation. So we can find the roots of the denominator using the quadratic equation. Which of course tells us that if we have a polynomial that looks like as squared plus bs plus c, then the roots of this polynomial are going to be s equals negative b plus or minus square root b squared minus 4ac all over 2a. Just a reminder of our quadratic equation. So for our general form of this transfer function, a is going to be the coefficient of s squared. So we have a 1 out here. It's an invisible 1. So for our general form, a is going to be equal to 1. B is the coefficient of s, so that's all of this here. B equals 2 zeta omega n, and of course that leaves c equal to omega n squared. All right, I'm going to leave it to you to chug through the mechanics of plugging this into your quadratic equation. Suffice it to say that our poles should have the form of minus zeta omega n plus or minus omega n square root of zeta squared minus 1. So these are going to be the poles of any second order system. Poles of any second order system. Give a little more space here. Okay. So I said that interesting things happen depending on the value of zeta here. So we're going to look at several very special cases. First thing I want to do is look at what happens if zeta is equal to 0. What happens if zeta equals 0? Okay, well, if zeta equals 0, this term becomes 0. So our poles, let's say our poles, S equals 0 real part plus or minus omega n times the square root of 0 minus 1, which is just the square root of negative 1. And the square root of negative 1 is just our imaginary number. So this is just I, or if you prefer the electrical engineering version, J. All right. So what happens is we end up with a purely imaginary set of roots. Purely imaginary. There's no real part. The real part is 0. So what I'm going to do for each of these cases of what happens to the poles is I'm going to draw our poles and our zeros on a pole zero map. So on the S plane. So we have real, imaginary. I'm going to draw it on the S plane, and then I'm also going to show you the general behavior in the time domain. Okay. So if we have purely imaginary roots, there's no real part, then on our pole zero map, our poles need to be purely on the imaginary axis, and they are plus or minus the same value, right? Plus and minus omega n. So the location of our poles is 0, omega n, and 0 minus omega n. And it turns out for a system like this, we are going to end up with oscillations. And I'm trying to draw these as consistent as possible, but I'm not very good at it. But these are oscillations that don't damp out at all. And of course, I'm talking here about a step input response. Just like we did for first order, we're going to be talking about the step input response to these particular cases. Okay, so we oscillate and oscillate and oscillate, and nothing ever changes to these oscillations. We call these types of systems undamped systems. Remember, zeta equals 0, there's 0 damping. So we call this undamped. We call this an undamped system. And that's going to be an important vocabulary word. All right, purely imaginary means undamped. All right, now let's look at the next case for zeta. What happens to our poles if zeta is between 0 and 1? What happens if zeta is between 0 and 1? Let's look what happens to our poles. Well, our real part no longer disappears. We still have this minus zeta omega n term. That part doesn't disappear anymore. And then we have plus or minus omega n square root zeta squared minus 1. Okay. In zeta squared, zeta itself is less than 1, so zeta squared is going to remain less than 1, which means that what happens under this root is always going to be negative. Always negative. Which means that we can actually pull out our square root of -1. I'm going to rewrite this as instead 1 minus zeta squared, and all of this is going to be times our imaginary number I. Okay, so I just pulled out the -1 that I know is there. I know there always has to be a negative under this root because zeta is always going to be less than 1. Okay, so this is a complex root, meaning that there is both a real part and an imaginary part. So we end up with a complex root. And in fact, it's a complex conjugate root pair. Complex conjugate pair. Okay, and so like I promised, let's put this on our pole 0 map on the S-plane. And we'll talk about the unit step response in the time domain. To erase this. All right, these roots have both a real and an imaginary part, so these roots are out to the left somewhere. And we can write the coordinates as minus zeta omega n in the real direction, and then plus or minus omega n root 1 minus zeta squared in the imaginary direction. So obviously this is the negative part and this is the positive pole. And for systems that look like this, the response will look something like this. So it turns out that anytime we have an imaginary component, we will have oscillations in the time domain. Imaginary component means oscillations in the time domain. But the difference between our undamped system and what we're looking at now with damping is that these oscillations will attenuate over time. These oscillations get smaller and smaller and smaller, and eventually they go away. And for these types of systems, we say that they are underdamped. Not undamped, but underdamped. Okay, so we call this an underdamped system. All right. And let's look at what happens when zeta is equal to another very special value. So we looked at zeta equals 0 as a very special value. Then we looked at an entire range of zeta values. And now we're going to look at another special value, which you can probably guess is the value that makes this root 0, which of course is zeta equal to 1. If zeta equals to 1, more special things happen. Let's look at our poles. If zeta equals to 1, I end up with a minus omega n. Minus omega n real part. And what happens to this other part here at the other side? So we end up with a 1 minus 1 is 0, which means that the square root of 0 is also 0, which means we're multiplying omega n by 0. So this entire term on the right-hand side just poof, it goes away. So we have no imaginary part. And this is actually a plus or a minus. So we're going to get what we call a purely real root or pole. And we're going to put this on our pole 0 map. And our time domain response to a step input. Turns out that when zeta equals 1, our time response of this system looks a lot like a first order system. And this is on the pole 0 map. We get this interesting thing where I'm on the real axis. Oh, sorry. This is not positive and negative. This is just a repeated root. It's not positive and negative. It is just repeated, meaning that we have something like s plus omega n times s plus omega n. So there are two roots co-located at omega n or at negative omega n. And so the way that we draw this on the map is something like this. We have a pole right on top of another pole. And this is, of course, minus omega n comma 0. We call this very special system a critically damped system. All right. Our very last case is basically all of the rest. So we talked about what happens when zeta is 0. We talked about between 0 and 1. We talked about the special value at 1. And now we're going to talk about zeta greater than 1. Now, some people in class asked, is it possible for zeta to be less than 0? And it turns out, yes, it can be for systems with energy injection. So zeta as a value greater than 0 talks about energy that is being sapped away from the system. It's being damped in some way. But if you are forcing this system with some energy injection over time, that forcing is going to show up as sometimes it'll show up as a negative zeta term. So it is possible, but we would have to start talking about systems that are forced. And right now we're just talking about unforced systems. We're just talking about what we might call the natural response of the system. So for zetas that are greater than 1, let's look at our poles. Well, our zeta term doesn't go away. It's some value greater than 1. So we have this minus zeta omega n plus or minus omega n root, let's go look again, zeta squared minus 1. Well, if my zeta is greater than 1, the square of that term is going to be greater than 1, which means that this is always going to be positive, which means that I don't have an I that I can take out. I can't pull out my imaginary number I, which means that these systems, they lack a complex part. Okay, so these are also going to be purely real. It's not going to be a repeated root. Actually, let me add that to this description here. Purely real, repeated. Whereas this one is purely real, but it has two distinct roots. It's not repeated. Because this part is going to be positive, there is no imaginary part. And so remember, we said that anytime we have an imaginary component, it's going to cause oscillations. This time we don't have an imaginary part, so we're not going to oscillate. And let's draw that on our pole zero map and our time response. This is time. So I have no imaginary part, but I have two distinct roots. So both roots are on the real axis, but they are separate from each other. And I can write these coordinates as minus zeta omega n plus or minus omega n square root zeta squared minus 1 comma 0 imaginary. All right, and then our step response looks really similar to being critically damped. There's no oscillations, it's just slower. It's slower to reach that final value. So this is slower than being critically damped. And we call this an overdamped system. All right, so we've covered all of our cases of zeta. We have an undamped, an underdamped, a critically damped, and an overdamped system. All right, and each of these has very particular time response behaviors. So underdamped oscillates forever with the same oscillation. Underdamped has an attenuated oscillation. Critically damped looks a lot like a first order system. And overdamped is a very slow response. Okay, just like for first order systems, we're going to define some time specifications. And we're really going to kind of hone in on these underdamped systems. Because these underdamped systems are kind of more interesting in a lot of ways. Let's look at our time specifications for second order systems. Now, several of these time specifications are the same terms as for our first order systems, but some of them are brand new. And in fact, we're going to start out with one that's brand new. This is what we're going to call our peak time. Our peak time. And in words, this is the time required to reach the first, which is usually equivalent to the maximum peak. So if we draw out our time response of an underdamped system, oops, that was supposed to be a T. We know that it looks something like this. We start out with a big oscillation that gets attenuated over time. That peak time is wherever this largest peak occurs, and that's in seconds. Now the formula, which you do not need to memorize, this will be provided for you, is pi over omega n square root 1 minus zeta squared. And part of this formula, I'm hoping, looks a little bit familiar to you. It turns out this denominator for our peak time is the vertical component of the underdamped poles. Whoa, let's go look at what I mean by that. So I'm going to go back to where we defined our poles for an underdamped system. Let's go back to this underdamped system here. This is our underdamped system. Let's look at these poles. Pole here, pole here. What sets the vertical component? This thing. This thing. Omega n square root 1 minus zeta squared. That is the denominator of our peak time. So what this means is that if you are designing your control system, which I want you to start kind of thinking about designing a control system as deciding where to put these poles on your pole zero map. That's what you get to do as the control designer, is place your poles on this map in places that achieve some desired behavior. So what this correlation means with the peak time, it means that as long as the vertical component of our poles is in the same place, our system will always have the same peak time. So let's say I am a control engineer and my boss tells me, hey, I want you to design a control system with a very specific peak time. When you go to look at your system and you start to decide where the heck should you put your poles on this pole zero map, you should say, okay, I am restricted to placing my poles on this vertical line that achieves my desired peak time. Now you can move left and right. You can move these poles left and right still, which is going to be related to a different type of behavior. You can move them left and right, but you have to be on this particular vertical location in order to achieve a particular peak time. All right, let's go back. That's all I'm going to say about peak time. The next time specification is going to be percent overshoot. Percent OS, we'll call this percent overshoot. In words, this is the amount that the response moves past the final value at maximum. So what is the maximal amount that it surpasses the final value? And then we express that amount as a percentage of the final value. Expressed as a percentage of the final value. So again, if we look back at our underdamped system response here, we're looking at how much does it overshoot, overshoot. How much do we go past? Whoopsies, all out of whack here. How much do I go past the final value, which is this dotted line, this line that it approaches over time? How much do we go past that at maximum? And then we express that as a percentage of that final value. Our equation here is percent overshoot is equal to e to the minus zeta pi all over square root 1 minus zeta squared. And then this quantity times 100. One thing to notice is that this overshoot only depends on zeta. There's no omega n's that appear in this. Okay, so you can set your omega n as whatever you want and still achieve a particular overshoot. Now let's go back to our pole zero map real quick. One thing that's going to be important to note is what is the zone, or what are the locations on this map that have a constant zeta value? It turns out that the constant zeta values are defined on these lines extending from the origin. So graphically speaking, any poles that lie on these same lines will have a constant damping ratio. And we often refer to these lines of constant damping according to the angle that they make with the real axis. Say these are lines of constant damping ratio. So lines of constant zeta. And in fact, we can say that zeta itself is equal to the cosine of theta for zeta values between 0 and 1. So these underdamped zeta values. Oops, need more space. Okay, we've got two more time specifications. We have, next we'll do settling time. Which has this exact same definition in words as we did for the first order systems. So this is the time for the transient oscillations to decay and stay within 2% of the final value. I can draw that. Underdamped system looks something like this. Wee, 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 wee. And then I'm wanting to look for that 2% envelope, plus and minus 2% from this final value, which is this dotted line. So if I go, this is not to scale, of course, but if I were to draw a 2% window like this, plus and minus 2%, I want to look for the point at which my system enters and stays within that 2% envelope. So that is obviously happening right here. So right here would be our settling time. Okay, my equation for settling time is a bit simpler than our previous specification. So this is zeta omega n, 4 over zeta omega n. And then what's interesting here is that this denominator sets the horizontal component of the poles. That's that horizontal component. Okay, and lastly, we're going to look at rise time. TR is rise time. Need to move this image down a little bit. Okay, rise time also has the same definition. This is the time to go from 0.1 to 0.9 of the final value. But for second order systems, we don't directly calculate this. We tend to actually look at a known relationship between the zeta value and our rise time times omega n. And this is the relationship that we know exists for these types of systems. We have 1 and 3. We have 0.1 and 0.9. So what we do is we find out what is the zeta for our system. What is our zeta value? We find that on the x-axis. Let's say maybe we found that our system has a zeta of 0.5. So I look at where is this relationship at for a zeta of 0.5, and that gives me TR times omega. So let's say maybe this is, I don't know, 1.638. So that means that this is 1.638 is equal to TR times omega n. So if I want my rise time, I then need to divide that number by omega n. So if my natural frequency was maybe 10 radians per second, I would get that my rise time is 0.1638 seconds. Okay? Better yet, it is a little bit imprecise to read numbers directly off a graph. So what we do instead is we have a table of numbers. And so that's actually what I was looking at a second ago, is I said, okay, I have a damping ratio of 0.5, and I read off the table what is the normalized rise time. So normalized rise time means that this is TR times omega n. And so to find just the rise time, I need to take whatever value I read off this table and divide by omega n. All right, and we're going to make this a little bit more concrete by doing an example. All right, so let's do an example. Let's say we have this transfer function here, 100 divided by s squared plus 15s plus 100. And I want us to find the peak time, the percent overshoot, the settling time, and the rise time when subjected to a unit step input. To do this, we know that our equations for peak time, percent overshoot, settling, rise time, all of those are functions of omega n and zeta. So that means we need to find out what the heck is omega n and what is zeta for this transfer function. So remember, we can write our general form of this second order system as omega n squared over s squared plus 2 zeta omega n s plus omega n squared. And if I compare that to the transfer function that I gave you, I can clearly see that omega n squared is equal to 100, setting the numerators equal to each other, which means that omega n is just equal to 10. Now it's really equal to plus or minus 10, but for these specifications, we're only going to consider positive frequencies. So we only need to worry about the positive 10. And this is in radians per second. Okay, now we need to figure out zeta. So zeta is determined by the coefficient that multiplies s. So we can say that 15 here is equal to 2 zeta omega n by comparing the two forms of the transfer function, the general form and the specific transfer function given. I know that omega n is equal to 10, which means that zeta has to equal 15 over 20, which is equal to 0.75. So these values we will plug into all of our equations for the peak time, percent overshoot, settling, and rise time. Okay, so it really is as simple from here on out as just plugging and chugging in these equations. So I'm going to go pretty fast here. I'm going to say the peak time equation was this one here. If you plug and chug, you should get 0.47 seconds. My percent overshoot equation was z equals minus zeta pi over square root 1 minus zeta squared, quantity times 100. Plug and chug, you should get 2.8%. My settling time was 4 over zeta omega n. You should get 0.53 seconds. And lastly, the rise time. Remember, we need that table for the rise time. So I'm going to go copy and paste this guy. Copy. Let's paste it down here. All right, so what was my damping ratio? That was 0.75. So our table only has 0.7 and 0.8. So I'm really just going to estimate here. I'm going to say I know that my normalized rise time is roughly halfway between these two. So let's say that TR times omega n, the normalized rise time, is roughly equal to somewhere between 2.1 and 2.4. So we'll call it 2.3. But now, to find the actual rise time, we need to divide this number by omega n. So TR is roughly equal to 2.3 divided by that 10 radians per second natural frequency. So this is equal to 0.23 seconds. All right, that's it, folks. Those are all of the time specifications for a second order system. All right, thanks for joining me. Sorry again about the recording issue. Please continue to remind me to hit record and double check that it's working. And I'll see you guys Thursday. Bye.